Hello, my name is Joseph Tucker, and I worked with my partner Neil Reyes to help accomplish the Chem Processes project. This project is about the production of ammonia. The production of ammonia begins with a fresh feed of nitrogen gas, hydrogen gas, and inert gas. It then feeds this fresh feed into a reactor, through a cooler, into a condenser where ammonia is condensed and then pulled out as a liquid. Nitrogen gas is left over, as well as hydrogen gas, and inert gas is pulled back out. Some of it, a percentage of that, is purged off, and the rest is recycled back through the system. This is what our code finds out. It finds out how much ammonia is pulled out. It also finds out how much of the nitrogen is purged off, and then how much is overall converted into ammonia, or the efficiency of our system here. Now, we'll start off with our code. Our code starts off with inputting how many moles of gas you're adding to the system. This is important because you need to know how much you're adding to the system. Therefore, you can find at the end how much is coming out, because all we're working with here is percentages. Now you're going to enter the percentage of inert gas, the fractional conversion of the reactor, which is going to tell you what percentage of gas your reactor is actually going to convert into ammonia. The input, the fraction of gas purged off, so when it comes out of the condenser, all the gases come out of the condenser, how much will be purged off, and then how much will be recycled when it goes to the recycle stream. The rest of that will be recycled and sent through the recycle stream. Now, our function, after it receives all this input data, is going to take all this input data and send it through our function. Now, what our function is going to do with this data is it's going to take our moles, our mole fraction of inert gas, our fractional conversion of the reactor, and the moles purged, and it's going to pass it through a data check. Now, this data check is going to make sure that all of our mole fractions are actually fractions, things that aren't equal to 0, because none of these can be equal to 0, nothing is less than 0. And what it's going to do is check these things and make sure that they're not actually less than 0, equal to 0, or any of that. And in most cases, it's either going to warn you and say, hey, it's outside the accepted range, or if it's a negative value, it's going to convert it to a positive value. Now, what it does is it's going to find how much of nitrogen you start off with, and then how much hydrogen you start off with. Then it's going to pass it through the second stream, and it's going to figure out how much, after all this is converted, how much ammonia you have. And then, after it finds out how much ammonia you have, it's going to find out how much nitrogen you have left over after the nitrogen is purged. After the nitrogen is purged, you'll have this value, and then it's going to calculate the overall conversion of nitrogen. What's going to pass back is it's going to pass back the moles of ammonia produced. It's going to pass back the nitrogen purged. It's going to pass back the overall conversion of nitrogen, and then it's going to pass back a variable of nitrogen initial and hydrogen initial, which is what you're going to need later on in the code. Now, after this, the code is going to come back to the main script over here. And this is where we're going to start graphing. This is going to graph the first graph, which is the theoretical moles produced when you have a certain amount purged. This is a theoretical amount of moles produced of ammonia when you have a theoretical fractional conversion. The third graph is going to set how much inert gas is and how much moles produced of ammonia you're going to get from that. Now, our third task here is going to show us the process for making this more efficient, how we could make the ammonia more efficient, the production of ammonia more efficient, and how we could ultimately make the process a little bit better. Now, our fourth task is basically going to do the same thing as our first. However, instead of It's going to actually check the values in the main script, make sure they're all positive, just like the last one, no negatives, anything like that. And then we're going to take it, send it to the heat cost, send it to the function task 4, excuse me. And what task 4 is going to do, task 4 is going to take the values of moles, initial inert gas, fractional conversion, and moles purged, and it's going to figure out your ammonia and all that. It's going to figure out how much inerts, how many nitrogens, and how many hydrogens you're going to get at the end. And then what it's going to do actually is figure out how much it takes to cool it. It's going to multiply it by the moles, how many moles of this stuff are there. And in some cases, the fractional how much is purged, because what's purged off in the case of nitrogen, hydrogen, and inert is going to be how much is going to need to be cooled. And this is going to take how much is going to take to get the ammonia cooled down to where it can be condensated out. Now all this is just to show how much cost it's going to take to cool it. So what we're going to do is we're going to take a sum of all these values. This is all the heat. All the heat it's going to take to lower the value from 450 to negative 20. And then we're going to divide that by 100,000, which is a megajoule. Now the cost to heat a megajoule is $17.68. So you're going to multiply this by 17.68, and you're going to get the cost of cooling this amount per hour. Now we're going to come back to here, and what I'm going to do is show you it. Yes, F per F, and it costs heat cost. Now, would you like to input new values? What this is basically going to do is ask you if you want to input new values. You can put yes or no. Now, I'm going to show you the code running. Alright, so we're just going to take some theoreticals here. Input the moles of gas added to the system. So you're going to add 4 moles of gas to the system. Input the mole fraction of inert gas. So the mole fraction will be 0.33 for this problem. Input the fractional conversion of the reactor. Let's say the reactor converts 90% per pass. Input the fraction of gas purged. Say we're going to purge 50% of the gas. Oh, it didn't change the folder. My bad. Hold on just a sec here. Okay, we have to change the folder before we run it. Now we're going to add, again, 2 moles. 0.3 is going to be the fraction of inert gas. Input the fractional conversion. The fractional conversion will be 6. The amount of gas purged will be 0.5. And that is going to give us the overall conversion of nitrogen. Now, this is going to be how to make the process more effective. If I get this down from here. Figure 3 is just going to show us our graph of mole fraction of inert gas versus moles produced of ammonia, fraction leaving versus moles produced, and then fractional conversion versus moles produced. Now, these are all going to be linear. So what we found out is the process can be more efficient by maximizing fractional conversion. This could possibly be accomplished by running many small reactors that would have high fractional conversions. Purging a greater amount of this in this situation would be beneficial because it would create a greater ridding of inert buildup. Also, a low amount of inert gas would be optimal. Now, this is where it's going to input the molar flow rate. So this is going to take the molar flow rate, which we'll say is 3. 3 kilomoles per hour is going to flow through the system. Now, the fraction of inert gas is going to be 0.3. The fraction of fractional conversion of the reactor will be 0.6. The fractional gas purged will be 0.3, and the cost to cool will be $9,423.40. Now I'm going to say no, I would not like to put new input values, but this will roll back around and you can see it all again. Now let's do one more thing here. Let's see what happens when we run a negative value through the code. It should warn us that there is no negative values allowed in the code. Now mole fraction negative 0.2, 2.2, See, it warns us and then converts it back to positive. Limitations of this code involve a lot of units. You're going to have to change units before you get into this code, or else it's not going to work. You can't just put in moles, you have to put in a fractional number, because the way this code runs is it takes a fractional number and then finds everything based on a fractional number. So if you were to put something in here greater than 1, the code won't run. So everything has to be in the right values. That is one limitation of our code. However, it is a pretty good code and it's pretty useful. It can be used for many things. Thank you. This is Joseph Decker.